Okay, so the goal of the next half of the course is to get Maxflow algorithm exact and also approx. For the approx one, we're gonna show an algorithm with this running time. And actually, it could be improved to this one, but I will not show this thing. For exact algorithm, we will show an algorithm with this running time. Near linear, no, not near linear, but n square, so near linear in dense graphs. There is a way to, there is a very different approach that gives you this one, but it's gonna be too advanced. So I will not be able to cover it in this course. And it's like, yeah, the paper it's kind of 150 pages long, so yeah, cannot really talk about it in class. But this is possible, yeah. So this is already, this is a state of the art, and it's just put on arXiv yesterday, and I hope to teach this. Yeah. All right, so that's the goal. But one technique to do this one is push the level. Okay, it's really push the level. Actually, it's a practical Maxflow algorithm that people use, and it's really flexible, and it's kind of nice and versatile in theory and in practice. Now to teach this push level algorithm, I will actually start with something related, which is decremental shortest path. So you see some techniques today for decremental shortest path, which is actually interesting by itself. Okay? And there is a course of routine there that's going to be useful for push the level for next class. Yeah. Right. So decremental shortest path, that's the today topic. And so we're going to talk about shortest path. And let me start with one intuition. The intuition is that we can observe that gravity can compute for us a shortest path. Okay. How? Just imagine that you have a mobile, okay? Like a mobile, not a mobile phone, but a mobile with dots and string. Okay? There are like a bunch of things, and then you fix one dot, okay? One dot t. Imagine this, and then just hang dot t, like you fix it, and then let the gravity pull everything down. Okay. So this is a picture. This is a mobile. You have this. This is like you have a bunch of dots. This is the length of a string. Okay. And now, once you turn on the gravity, and you fix it at this, fix this thing fix the node t at position 0, then the gravity will just pull everything down. And then you see that some node will, some string will be tight, some will be not tight, like this guy. Yeah. But you see that, do you see that like the gravity really kind of reveal the shortest path for you? How? Just look at the string that is tight, that is not relaxed like this one. The thing that is tight is basically the shortest path to t. Like, so from this node to t, this is like along this tight edge and along this tight edge, and it's going to be the case that the shortest path from this yellow node to t is 4. This is the case for this node d here too. This shortest path here to t is 3. Yeah. And this one is not tight, so it's not going to be along the shortest path. Okay. So that's the intuition that is really good to keep in mind. how shortest path is kind of, you can just get the shortest path from this physical process. Okay, so shortest path to node T are on tight edges. But note, by the way, that this physical intuition, like when you have a string here, you think of it as directed edge, undirected edge, where like the direction from A to B, from A to C, and from C to A are just like the same. Okay. But in this class, we will talk about directed graph. Okay. So let's try to generalize this intuition to directed graph. So now you need to imagine a string that can only be stretched in one direction. Okay. Meaning that maybe this string is of size of length 2, okay, U and V. And if I pull V in this direction, and V is ahead of U by like a 2 unit, now it's tight. But if I pull V to another direction, then it's not tight. So only in one direction, okay, that it can be tight. Okay. So imagine this: you have a graph, okay, with edge length W. Okay. This graph is directed, and the edge length here, let's say, is integral. Okay. Now I'm just gonna put every node to some position with its label of U. Okay. It's just like put every node into the real line. Okay. Or you can think of it as a gravity that pull everything from point 0 to point below it. But actually, I'm gonna just draw it in horizontal way. Okay. Okay. And a directed edge here is going to be relaxed. We call it relaxed if U minus level of U minus level of V is not too big. So maybe think of it like this. Let me draw like a real line in a weird way. I start on the leftmost as 0. And I'm just going to increase number from 0. Like this is 1, 2, 3, up to maybe n or something. Okay. So this is a real line from 0 and increasing in number here. And an edge is relaxed if level of U minus level of V is less than the length. For example, if this guy have length 2, and I just, this is U and V. Okay. And if V here is just, level of U minus level of V here is just 1, but the length here is 2. So this is still relaxed. Okay. And also, this is like even if U is here and V is on another direction, it's relaxed too, because it's like one direction edge. Okay. But I'm gonna say that it's stretched if this thing is long, it's longer than the length. So for example, this one, okay, the length of this string is just 1, but I stretch it to be 2. So this one is stretched. So the difference in level here is 2, but the length is 1. And then it's tight, so it just means that it's both relaxed and stretched. Okay, so this is tight. Okay, is this terminology clear? And it shouldn't be just clear; it should be kind of intuitive to you. Okay. All right. So now, here is the statement that kind of review how like tight edges kind of is related to shortest path in a formal way. Okay. So imagine that all edges are relaxed, so you don't stretch any edge. Okay. There's no edge that is stretched like this. Suppose that all edges are relaxed. Okay. Then, all edges in the graph in G are relaxed. Okay. Then, for every pair of nodes U and V, I claim that level of U minus level of V is going to be at most the distance from U to V. Okay. So this should be intuitive, not just okay. Yeah, I explain it. Yeah. So this is the first statement, which is that if there is if the distance from U to V is something that is the shortest path from U to V, then you cannot stretch the position from U to V by more than the distance. Okay. Okay. And next is that if there is a stretched path, meaning that for every edge in this path, every edge is stretched. Okay. If there is a stretched path from U to V, then, well, the level of U is further from the level of V by at least the length of the path, because they are stretched. And then I'm just gonna claim also that this path, if this is true, if both of this is true, then you know that P is the shortest path. Because I'm gonna prove this and prove this soon, okay? But it could be just intuitive to you already. But assuming this and this one, then it means that the length of the path P is at most the distance from U to V, right? Combining the two things. So it means that P is the shortest path. And also, the difference in level of U and V is exactly this distance. Okay. All right. Why is this? Because you know that P is sandwiched between level of U minus level of V, and this is just some path. So this path is at least the distance from U to V. So everything here is kind of sandwiched. They are all the same. Yeah.
When you say P is stretched, you mean like every edge on P?
Every edge on P is stretched. Okay. So let's try to prove these two. Okay. These two lines. Okay. So imagine that you have a path P, right? Path P from U to V, and let me write it like U1, U2, U3. Yeah. And let's say this is V. Okay. Now, you know that every edge is relaxed. Okay. So what you get is that like the level of U minus level of V, you can write it down like level of Ui minus level of Ui minus 1, summing over all edges in the path, because they just telescope to this thing. But if every edge here is relaxed, then the difference between level here is at most the length. Now you sum over all this length, then you get that this is just the length of the path. Okay. So for any path from U to V, you know that you cannot stretch the position from U to V by more than the length of the path. Okay. And this is true for shortest path as well. Even for shortest path P star. So it means that you cannot stretch the position from U and V by more than the length of the P star, which is the distance. Okay. So that's why this is true. Do you see this intuitively? This should be not mathematical but physical, like what you feel. Okay. Right. Okay. And then next is just that if a path is stretched, then you know that the position from U and V is stretched longer, at least as long as the length of the path. And here's just the same proof. Like if P is stretched, then you write down the position of U and the different level of U and V, like here, sum over all edges here, and each of this is stretched. So it's at least the length. And this total length is just the length of the path. So you know that U is kind of far away from V by at least the length of the path, if the path is stretched. Okay. So you get this one. Okay. So again, you get that if every edge is relaxed, then you never stretch any pair of nodes by more than its distance. And if you have any stretched path, then now you really just stretch the two pairs, the two nodes, as big as the length of the path, which means that path is the shortest one. Okay, good. Okay, so now we can actually put some parameter to this notion of relaxed and stretched edge. Okay? So basically, you think of this string as maybe an elastic string where you can stretch really a bit. Okay? So now I can say that an edge is alpha relaxed. Maybe think of alpha as 2. Okay? Where if this is like at less than the length by alpha, so you might stretch it by like a factor 2. Okay? It's still 2 alpha relaxed, and it's beta stretched if and think of beta as maybe 1/2. Okay? If this difference is at least beta of the length, so you don't stretch it fully, but stretch it somewhat. And it's gamma tight if just the same, just like it's exactly gamma here. Okay. And you can say the same thing, almost the same thing, that if all edges are alpha relaxed, you don't think of alpha as 2, right? Then now for any pair of nodes, you never stretch it by more than 2 times the distance, or alpha times the distance. The same proof. Just that you have alpha here and alpha here. And so you get alpha and alpha here. And also if there is like, it should be, if there is a beta stretch path, like a path where every edge is beta stretched, then this different level is at least beta times the length. And then it would mean that this path, and here how to prove this? Just the same proof, right? You have that if P is beta stretched, then you get that this thing is at least beta here and beta here. Are we good with these two statements? So yeah, having these two, it just implies that the length of P, this thing, is at most alpha or beta of the distance from U to V. So P is going to be alpha or beta approximate shortest path. So it's shortest up to this factor. And you also know that like the difference in the how much U and V are stretched is just kind of sandwiched between some factor of distance. Okay, good. So this is like kind of the intuition that you should have in mind. How like once everything is not too stretched, like everything is quite relaxed, then the stretched path will reveal you shortest path. Okay. We can like have some notation. Once we fix the label, we can say that okay, this is an edge with respect to this label L, that is alpha relaxed, and this is edge set with respect to label L, that is beta stretched, and this is tight, gamma tight. Okay. All right. So having this intuition in mind, now here's a core data structure. Okay. This is like to maintain tight edges when you change the label. Okay. It's going to be important data structure that we use for both dynamic shortest path today and MaxFlow for next class. And motivation is this. Like, imagine that you have a graph, and this graph is not, it's like undergoes some, you have a graph and label L, and there are change, like you're gonna only increase label. You only increase label. So kind of thing like gravity kind of just keep pulling some node more and more. But you don't pull everything at the same time. Just that it's given to you as an update to pull some node more and more. Okay. And the graph can change too. So you can like add new string and remove some string. Okay. But we will make sure that at all time all edges are relaxed. And once all edges are relaxed, then what we want from this data structure is that we want to identify which edge are stretched, because they are useful for shortest path. That's what we want to do. Okay. So here's a definition. The tight edge data structure where you're given G, the label, the graph, the label, and some maximum label H. Okay. So there's going to be two input, which is a graph with some weight. This is directed graph. And label that map everyone to number, integer number, and you have maximum label H. Okay. H here is a parameter. And what we want to maintain is something that we call active edge. Think of it as like a tight edge. The thing that is tight, active, is tight. Okay. And for every node, we will maintain this edge active set explicitly, and like it should be explicit in the sense that for every node kind of knows all the active edges going out of it. Okay. So every node maintains the active edges out of it. In literature, they call this thing admissible edge. If you want to look up. This is like what they call it, but it's less. It has less physical meaning. So I want to use something that is more intuitive. And how this is dynamic input, so things can change. Okay. So here's an update that you can do. You can relabel U, meaning that you increase U. You move U to the left. Okay. So remember, like this is like this point is 0, and this is like H, and you increase U by 1, like level of U to level plus 1. Yeah, L and L plus 1. This is to relabel, to pull like the gravity pulls something. Yeah. But I will call this only when there is no active edge incident to you, out of you. Because you should think of this active guy as like some tight edge. This is like an active one, it's like tight edge. So if this is you, and there is some tight edge of you to some V, this is kind of tight already, so you cannot pull it. Okay. Like I will not allow pulling you if you is tied with someone else. Yeah.
So for each vertex, is the set of active edges that are coming out of you just like the saturated edges, or like what do you call it? Like the
Tight. Yeah.
Okay.
Yeah.
So-
it's stretched one. Yeah.
But tight is different from stretched, right?
So it's gonna be both tight and stretched because okay. Yeah, it's gonna be both tight and stretched. You'll see soon. Yeah.
Is there ever going to be an edge that's like stretched but not tight, like very far, like far stretched?
No, because I will promise that everything is relaxed. So if it's stretched, it's tight. Okay. Okay. So this is like what we can do to pull to relabel edges, increase level, and you cannot do it if there is some active guy on you. Okay. And also we can change the graph. You can delete some edges or insert a relaxed edge. Okay. So why I allow this? Because my invariant is that I want that in this data structure, all edges need to be always relaxed. All edges is just relaxed. It's one relax. And another invariant is this, where I set it this active. So an edge is active just means that an edge is stretched. Okay. So every active edges, the set of active edges is just exactly the edges that are stretched. But because every edge is relaxed, so if it's stretched, then it's tight. Okay. Question about this definition. It's just like we want to maintain a graph and label such that everything always is always relaxed, and we want to identify E prime, which is exactly the guy that is stretched, or it just means that it's tight. And the change can be that you keep pulling nodes to the right, and you can add some new edge too, but you can only add relaxed edge so that you never introduce the edge that is too overstretched. And you can delete things. That's okay. Yeah.
Is there any runtime constraint?
We're gonna show how to solve this and prove runtime. Okay. Okay, so we can basically maintain this E prime, which is this tight edge data structure, output from the, like you think of E prime as a set of tight edges. Okay. We can maintain the set of these tight edges under like the graph and label that undergo change. Okay. And they satisfy this invariant. In time, MH plus U. U is just a number of edge update. In this class today, U is just going to be edge deletion. So, and there are M many edges, so think of U as at most M. Okay. You only delete edges. So, like for this class. So U is at most M, so U here is small. Okay. And M here is just the number of edges ever appear in G. In this class, if you only delete edge, then M here is just a number of edges initially, in the beginning. Okay. But in general, you can allow inserting edges too. Okay. And like in that case, if UV is inserted, then deleted and inserted again, I just count UV as one edge. Like it's just a pair that this pair appear in the graph, and that count as one. Okay. So that's what we want to prove. We can maintain the tight edges in time MH, basically. So basically, we spend time per edge, H time. Okay. So how? It's going to be really simple. The algorithm is really straightforward, like supernatural. So the idea is how do we maintain the active edge? Well, we kind of keep track on each edge. Whenever the level of the edge, the level of the endpoint of this edge change, then we probe the edge. What do I mean by probe? I mean, I just check if it's stretched or not. If it's stretched, then I mark it as active. If it's not stretched, then it's not active. So you have an edge. And suppose that I know now it's active or not. It can change from being stretched or not only when the endpoint of it change. Okay. And I just said that if the endpoint of it changed the level, then I probe it. Okay. So this is like, let's just do the straightforward thing. Okay. All right. And now, with this, I can relabel easily, okay? And the edge update is also trivial can be trivial and can be done in O1 time. Okay? Because if I want to relabel U, okay, I really just kind of increase the label. So maybe I relabel U, I increase the label, okay? And then every edge incident to U, now I need to probe them. Okay? And if I need to insert or delete an edge, well, then I just insert that edge. If I delete an edge, that's okay, just delete it and do nothing else. If I insert an edge, I can insert and just check if it's stretched or not. Okay, so it's just straightforward or constant time. All right. So you see that the total running time here is just going to be MH. because each edge can be probed at most 2 hash time. Because the level on the endpoint U and V can change hash time, and you pay hash per the endpoint. So you just probe each edge 2 hash time. And the number of relabel is at most n hash because there are n nodes. And each node can be relabeled hash time. And let's assume that n is at most m. So this is m hash again. And the number of edge update is u. And each take just constant time. So the total running time is just m hash plus u. And now let's we need to prove that the invariant are always maintained, but this is kind of quite straightforward. Okay, so let's see. Let's prove that every marked edges, every active edges, okay, is stretched. So why is that? Well, it's kind of don't need to prove much. Like we mark edge as active whenever it's stretched, because whenever the edge can be stretched, we check it, we probe it, and we mark it if it's stretched. Okay. And also, and why every edge is always relaxed? Okay. This is less trivial. The reason is that once some edge become active, once an edge become active or is stretched, if this edge is like active, if an edge UV here is active, so UV is in E prime. Okay. Once it's become active, that's when it's like stretched, right? But if whenever it's active, we will never relabel U. We will never pull U like to the right. That's our promise, right? If U is incident to some active edge out of it, we never pull it. We never relabel it. So we never like relabel U. So we never increase level of U. So E would stay relaxed until this is not active. But if it's not active, then like it means that it even have some slack. It's like, so then E will not be, it's even less than 1 relax. Okay. So once it's active, you never make it stretch, overstretch. And you wait until it's not stretched. It's not like, you wait until it's not active. And then it's even more than 1 relax, like less than 1 relax. So everything is stay relaxed. Okay. Are we good with this? Okay. By the way, this might be like some like maybe it's good to see this. Like, so basically, as long as the level of U is fixed, okay, the set of active edges going out of U is the decremental set. Okay. So you have active edges here, but some is not active because some maybe like is kind of relaxed like this. Some may be tight or stretched like this. Okay. But the set of tight edges incident to you or stretched edge incident to you, the active one, will be decremental, as in it only shrink. Why is that? Because as long as the level of U fixed, everyone else keep increase the level. So things only get more and more relaxed for all edges going out of you. Okay. So it's the decremental set. All right. Okay. And with this now we are kind of ready to get to. We're gonna use this data structure for maintaining tight edges to show shortest path algorithm. Yeah. Question?
So just to be clear, that edge there, for instance, wouldn't be included in the active set of V, just in U?
Yeah. Right. Like for every node U, we maintain like active set going out of U. Yeah. So this is not even like out edge of V. So it's not in the V list. Yeah. Okay. All right. So now I'm gonna show you an algorithm for maintaining shortest path. Okay. So this is one of the most basic dynamic algorithms, and here's the problem statement. Okay. You have, let's say, an unweighted graph for now. Every edge has weight 1, and you have a sink T, and you only delete edges. You have a graph and keep deleting edges. And what you want to maintain is a single sink shortest path to T. Okay. So you have T. Think of T as at level 0. And you kind of want to have single sink shortest path to T. Right. Okay. I will not motivate it too much. Like, shortest path is important. Dynamic algorithm is natural. And here we're just going to see the most basic way to maintain shortest path in dynamic graph. Okay. So here is the idea. The idea is that what will happen once every node except T, except the sink, has one tight edge going out of it. Okay. We learned before that, like, if you have a tight path or stretch path, then that path is shortest path. Okay. And if every node besides T has some tight edge going out of it, if U has some tight edge, V has some other tight edge, U prime has some tight edge. But this guy needs to have some tight edge too. Everything has some tight edge going out of it. At some point, it needs to go and reach T. And all these things these are all tight or all stretched. So everything will be shortest path. So that is going to be a shortest path tree. That's the intuition. Okay. So what we want is just, as the graph undergoes deletion, as long as for every node, you can maintain one tight edge going out of it, we are good. We're going to get the single source shortest path. So here's the algorithm. Okay. I just initialize the level of everyone to be 0 in the beginning. So everything is like at position 0, and we just kind of gonna keep pulling. We kind of play the gravity. We keep pulling everything. Okay. And we let this data structure to maintain the tight edges for us. We have G, we have level that we will keep increasing this level. And let me set the maximum level to be 2n. Actually, anything more than n is good. N plus 1 is fine. N plus 2 should be fine. Okay. And we can maintain this forest T. What is this forest? It's just a forest that you can get when every vertex, which is not the sink, every vertex you choose one edge, one active edge going out of it, if it exists. In the beginning, every node is at position 0, so there is no active edge in the beginning. But once the active set is not empty, then this is a forest that can be defined from the active, when every node choose one active edge out of it. Okay. So what we're gonna do is just this. When we delete an edge E, just delete it. But what we're gonna maintain at all time is as follow. As long as there is some non-sync node T, whose level is less than H, which is 2n, and as long as it doesn't have a tight edge out of it, then just pull it. Then just relabel it and play the gravity, you pull it. Okay, that's the algorithm. Any question about the algorithm? Okay. So, yeah, that's it's quite simple, and so let's analyze it. Why this is good? Okay. So once the algorithm stops, okay, then if some node can have level H, because we keep increasing level as long as level is at most H. Okay. It's less than H. But some node can have level exactly H, because if it's level H, we never increase it further. Okay. But for this, if the level is H, then I claim that actually there is actually no path from U to T. Okay. Why is that? This is just because, okay, first of all, the level of U is more than n, okay, because it's at least H. But the level of T is 0. Okay. So the difference between level of U and T is more than n. But at the same time, we know that every edge is relaxed. So how much you can stretch between U and T? At most a distance, because every edge is relaxed. You see this? Okay. So this just means that the distance from U to T is more than n. But this is undirected graph, unweighted graph. So if the distance is more than n, there is actually no path from U to T. Okay, so the guy, some guy can reach level H, but those guys are just the one that don't have path to T anyway. What about a guy that that have level less than H? We know that this guy will have some tight edge out of it. Why? Because we will never stop as long as it's level less than H and the tight edge is empty. Okay. So everyone that have level less than H or is can still reach T will have some tight edge going out of it. So now it means that we get to this picture where something is not reachable, cannot reach T, but the guys that can reach T have some tight edge going out of it. Okay. So this is gonna be a tree rooted at T and span all vertices that can reach T. And this is our stretch, because it's because they are in active set. It's stretched, it's tight. Okay. And these are all edges on a tree that is tight, so it's a shortest path tree. Okay. So don't need to read this. Like, is it clear to you that this is going to be shortest path tree? Are we good? Okay. Right. And so the total update time is at most, like U is the number of update is at most M. And the type H data structure has running time MH plus U, so that's MN. Okay. So that's it. We are done with like one very classical algorithm. This is by Even, Chilog, since '88. They didn't present it this way, but like this is the idea.
Can you extend this to like graphs where the weights are like unit capacitated or something?
We can, yeah, that's the next. Like, let me first, before go to weighted graph, let me ask you this. Like, do you see, what if we just want to maintain like, let's say an in-ball to t, where like the distance is up, like all the node that has distance up to h to t. We used to maintain just the shortest path tree, but what if I just want to maintain every node that can have distance up to h? Sorry, I want to maintain all nodes v, where the distance from v to t is at most h. What do we need to do this in time mh? Let's think of h as 10.
We can just set H in the tight edge thing to be like whatever that thing is plus 1.
Exactly. Yeah, maybe I should write this as x. Yeah. And what we can do is like set this thing to be x plus 1. So then the running time is going to be x, and this is going to be x. Okay. So if we just want to maintain a set that like are close to t, that is even faster. Okay. What if the graph is weighted with maximum weight W? If we just run this same algorithm, what's the running time? Well, when the graph is weighted and maximum weight W, then the distance to t can be as big as nw, right? So we could set h to be nw, and then the running time is this. So it's just gonna work, but w is big. W could be really huge. Could be like n to the 10 or something, like really big. So we don't want that, and let's try to split this up. Okay, so the next goal is like to work on weighted graph, but maybe we pay some approximation, but running time is still something like mn. Okay. So here's the problem. I have now weighted graph. It has weight now, but I have parameter d and epsilon. The graph still undergoes edge deletion, but what I want to do is just maintain kind of approximate ball of radius d. I think like this is t, and I want to get approximate ball of radius d, but up to something like plus minus epsilon. So I want this ball such that everything that is in distance, like that can reach t with distance d, it should be in the ball. And if it's in the ball, then it's not too far. It's like within 1 plus epsilon d. Okay. Like it's the approximate ball of threshold d. Okay. So this is the goal. Okay. It's like approximation for distance threshold d. And you can imagine that if you can maintain this thing, now you can like do some meta research and really get like the approximate distance just by having many thresholds. So let's solve the threshold version first. The algorithm is just here. Okay. Initialize the level to be 0 on everyone, but here's the key. I'm just gonna work with a new weight function, w prime, where w prime is kind of a round up version of w. This thing denotes w round up by this factor, meaning that it's just w, and I just round it up so that it's a multiple of this number. So, like if, let's say for example, 10 round up to be a multiple of 4, this would be 12. Yeah. Okay. So this is clear, right? I just round up w to be some multiple of some big number. You should think of d here as something huge, okay? You shouldn't think of d as something less than n. You should think of d as maybe like n cubed. Because this algorithm is slow when the distance, the weighted distance is big. And we try to speed this up. Okay? So you think of d as like something really big. And so we are kind of rounding up this thing to be multiple of something big. Okay. Right. And what I'm going to do is just maintain tight edges again. So we think we have a tight edge. Okay. And my set B, it's just going to be all vertices whose level is at most 1 plus epsilon d. Okay. And the algorithm is now almost the same. When I delete some edge, just delete it. And as long as there is some node whose level is not maximum, and there is no active edge out of it, we want to have active edge out of it. So we're just gonna pull it, relabel it. But what I'm gonna do is I'm just gonna relabel it by this much in one go. So think of this as basically I kind of scale up, like the weight used to be integral, now it's like a multiple of something big. And the level is now the multiple of something big too. Like everything is just multiple of something big. We just work in like kind of much coarse grain, like setting. Okay. Okay, so now, why do I want to round up everything to be a multiple of this factor and level is a multiple of this? Because it should speed things up. Okay. The edge weight here and the level, they are multiple of this number. Let's call it like k for now. Yeah, it's multiple of k. Okay. Why do you think this would speed things up?
We're again assuming that D is pretty large, so instead of having to do like a bunch of updates to get to the top of the level, what we're doing is we're doing it in large chunks, so we should still need about n updates.
Very good.
Learn that it's unreachable.
Yeah, like our maximum height, maximum level is D, is like 2D. It used to be that like we start with 0 and we might get to 2D. And like if you have like many steps here, it's just like 2D steps. But what we're gonna do here is just that, just jump in, jump. What? Okay. and this is like, this length is like epsilon d over n. So the number of jumps here, number of jumps is something like 2d over epsilon d over n. That looks like n over epsilon. Okay. So it just reduces the number of jumps because we work in the more coarse-grained setting. Okay. Yeah. So basically, this reduces the total update time of this tight edge data structure. By how much? By the factor that k. Yeah, the factor that we. Yeah, exactly. So basically, what this gives, it gives us the running time, the total update time of tight edge data structure is still mh, but over this factor. So what is this? Like, h is 2d, sorry. So we get that this is mn over epsilon.
Sorry, how do we know that choosing h equal to d is enough? Like, what if the weights are really large?
We're gonna show the correctness soon. Yeah. Right now it's just update time. Okay. So this is just mh over mn over s epsilon, and this is m even. Okay. So running time is good. Let's prove correctness. Okay. So what we know so far is that as long as the level of a node is less than maximum level, then it's gonna have like an active edge out of it, right? And we can conclude that the level of that node is just the same as the distance, but it's the distance with respect to w prime. Okay. Are we good here? Like, as long as it's not at the maximum level, it has some active edge out of it. And so, like, yeah, it has this active edge going out. But this is active, like this active edge set is with respect to its tight edges for the data structure where the weight is w prime. Okay. So this is like everything here whose level is less than h have shortest path 3 with respect to w prime to t. So, and the level here is 0. The level of t is 0. Level of t is 0. And level of v is just the distance from v to t. Okay. This is the same. So now I need to prove two things. That is, if v is in the ball B, where this ball, the one whose level is not too big, then if v is in the ball, then the distance in w, not w prime, is also small. And vice versa, if the distance in w is small, then it's in b. Okay, so let's prove this too. So first, if v is in the ball, just by definition, level is less than this much, which is less than h. But if it's less than h, then the level is like exactly the distance with respect to w prime. So w prime here is less than this much. How can you now conclude that the distance in w is less than this? Is w prime is small, is distance in W prime is small, while distance in W is small.
That because W prime are rounded up.
Exactly,
Distance that like in real W is less than distance in W.
exactly. W prime is like something that is bigger than W. So if the distance in W prime is small, distance in W is small too. Okay, good. So we're done. How about this one? If the distance in W is small, why must it be in in the ball? Okay. So the intuition is this: if the distance in W is small, to say that V is in the ball, I need that like level is small. This is like if and only if here, right? To say this thing, I need to say that, okay, my claim is that if distance in W is small, distance in W prime is also quite small. Because I want to say that in W prime, you don't increase it by too much. And if distance in W prime is small, then it must be in B. Okay, let's prove this formally. So suppose that P is the shortest path with respect to W with the real, like original weight. Okay. But let's see how much W prime increase the weight of P from W. Like W prime will increase the weight of W, but by not much. Because W prime here, like it's just at most the weight of W, but we round up something for each edge. For every edge in the path, this is the number of edges in the path. We round it up by this much. So you pay more by this much per edge. Make sense? But how many edges can there be in the path? At most n, trivially. So this term is at most epsilon d. Okay. And so this is at most epsilon d. This is at most d because the distance is at most d. So this is at most 1 plus epsilon d. But we know that the level of V is at most W prime of P. Actually, can someone tell me again why this should be the case? Why the level of V is at most the weight?
Because all of the paths, all of the edges in the path have to be stretched. So that we get.
Exactly. We need, this is, in this direction is because it's relaxed, right? Like we have that this thing minus this thing. We don't stretch from V and T by more than any, if this is like a VT path. For any VT path, we don't stretch it. This path is relaxed. So this is at most the weight in W prime of P. But level of T is 0, so we get this thing. But it just means then that like the level of V is at most, the level of V is at most 1 plus epsilon D. So V is in B. Okay. Good. All right. So what we get so far, we can basically distinguish if if the distance is at most d, or the distance is a bit more than d by some small factor in time, which is like mn over epsilon. Okay. What if we don't want like a threshold version? We just run the algorithm for all the threshold. Like just run it for this threshold d for all power of 1 plus epsilon. And with this, now you can just approximate the distance for every node, for every distance scale, up to 1 plus epsilon factor. And then the total running time is going to be this much for each scale. How many scales there are? There are at most nw, like that's the maximum length. And the base is 1 over epsilon, so this is, you get this one. Okay. All right, so that's how you get running time, which is something like mn, and something like log w instead of mnw, just by paying some approximation. Okay. And here's some exercise I want you to do offline. That is, suppose that distance, I call this thing h-hop distance from B to T. This is just the shortest path, shortest length among all h-hop paths from B to T. So it's just a, among all paths that contains at most h many edges, take the one with minimum length. Okay. So if this is like, if h is n here, it's just the same as distance. But if you restrict yourself to the one whose number of edges is at most h, then it could be a bit bigger than the real distance. So I want you to design an algorithm that maintains the ball such that if h-hop distance is at most d, then it's in the ball. But if it's in the ball, then the real distance is not too big. Okay. And the running time should be just mh. So think of h as 10, so this is even faster. Okay. So yeah, try to think how would you modify this algorithm so that the running time is mh. All right, but let's reflect a bit. How did we get this speed up, right? Because this is just much faster than MNW. And the key idea is that we basically, what happened is that we probe edges less often. Like in the tight edge data structure, what we do is just whenever some endpoint of an edge change the level, we just probe it, check if it's still stretched or not. Okay, but what we do effectively, what we are doing here is just that we probe it less often. We only probe it once, level change by this much, by this big factor, because we just force ourselves to jump by this multiple factor, like multiple of this factor k. And when this is big, this is just less often. Okay. But okay, so this idea basically is the key idea. Just probe things less often. And how to probe things less often? Just round up everything to be like some multiple of big factor. But we cannot round everything up by too big. Because why is that? Like if we round everything up by something too big, then the error that we get is even bigger. We just need to round it up so that at the end, when we pay this additive factor of rounding up, this whole thing is not too big. Okay. That's why like this factor is just need to be like small enough. We want it to be big as possible, but it need to be small enough so that this thing is just epsilon of d. Okay. Is this idea clear? Okay. But you see that this idea is such that every edge is going to be probed with the same frequency. It's just less often. You just probe it with like this frequency. Okay. Next idea that will make everything even faster is that we don't need to probe every edge with the same frequency. Basically, some edge, like try to probe each edge as less frequent as possible. The frequency can be different. Okay. And this is a way to speed things up from something that looks like mn here to something like n square, at least on the DAG. Okay. Okay. And how to do that? That will basically lead us to like another tight edge data structure that is now approximate version. Okay. I will go through this next time instead. Yeah. But the point is that it's going to be something that is similar to tight edge data structure, but now instead of having that every edge is always one relax. Now I allow some slack. Every edge just need to be 1 plus epsilon relax. So it can be a bit stretched, a bit overstretched, but it's not too much, like just epsilon. Okay. And the active set that we want to maintain is not just going to be all exactly one stretch edge. It's just going to be something that is kind of almost stretched, like maybe 1 plus 1 minus epsilon stretch. So everything is kind of approximate. And once we allow this approximation of being relaxed, like things can be a bit stretched, overstretched, can be the active one may be like a bit relaxed. Then it allows us to probe the edge with large weight less often. And this will lead us to the speed up. And this n square factor is like the reason why we get max flow, the final goal of max flow with n square running time. That's the reason. But we're going to learn this key data structure next time. Yeah. So questions before we finish?
So is there no relationship between today's algorithms and like cut matching game or like any of the stuff from like last week and stuff?
So once we learn about push level, and all this thing, we're gonna plug it into cut matching game.
Oh.
How the cut player is still like the random projection thing,
Yeah.
but the matching player, we used to use black box max flow algorithm. Now we're gonna not use black box. We're gonna use our own push level algorithm to implement matching player. Yeah. So once we learn push level, we're gonna now, like until push level, everything is kind of independent. But once we learn it, now it kind of merge the two branch, and now we get everything like fast, yeah, without black box. Last question. All right, yeah, see you next time.